Good morning. Good morning. We're going to get started. So this clock is off. They did fix that clock, so now I have a real clock that I can look at so I can make sure we're on time. We're going to continue talking about Lewis structures and resonance structures. Are there any questions before we get started? Anybody? All right. Okay, so we were talking about drawing a Lewis structure for this positively charged species here. And we added up the electrons, and I encourage you to do that at the beginning all the time to make sure you're drawing things right, but especially when you have things that are negatively or positively charged. It's really easy to draw the wrong structure if you don't count electrons. So we saw that we could draw it two ways. We distributed all the electrons. We put both the electrons on oxygen here because oxygen is more electronegative than carbon, and we left carbon without an octet. We can draw it that way. Or we could just take one of these lone pairs and now make, because we have this carbon without an octet, we have a lone pair, we could move that over. You can actually draw arrows for that. It kind of helps you when you're drawing resonance structures. We can move that over, and then we can draw this resonance structure here. So we have two valid ways of drawing this structure. And so what that is, that means that these are resonance structures. Okay, when we have more than one way that we can draw a compound, they're resonance structures of each other. And what we did is we used curvy arrows to show the movement of a pair of electrons. And curvy arrows are not something you do in G-Chem at all. They're a very big deal in organic chemistry. So I'm starting them early. We're going to be doing more in Chapter 2. And by the time you get to 51B, you'll be using them all the time. But there's some rules for curvy arrows. They show movement of a pair of electrons. So if I have a double-headed arrow here, a normal arrow, then I'm moving electrons to this location. So I'm taking this lone pair, and I'm moving electrons halfway in between this carbon and oxygen to make a new pi bond here. And we'll talk about that pi bond coming up soon. The tail begins at the current position of electrons. It always begins at a pair of electrons, and the head is the new position of the electrons. So it's sort of a shorthand way of describing where the electrons are moving, where they're coming from, where they're going. All right, so on the next page, important points about this example. Formal charge must be assigned to any atoms that have a formal charge. That's very important in organic chemistry. We talked about how to calculate formal charge. The sum of all the formal charges in the molecule must equal the overall charge of the molecule. So we want to make sure when we're drawing resonance structure that our charges are matching up. So we have a positive charge on carbon. Here we have a positive charge on oxygen. The overall charge is +1 for each of these. So we want to make sure we take a look at that. Overall charge is plus, and over here overall charge is plus. All right, so we talked about a formula to be able to calculate formal charge. We can also, and I said you could do it two ways. You could use the formula. You could memorize the chart with charges. You can do that. The other way to do it is, of course, we can take a look at this carbon here. We know carbon has 4 bonds, so this has to have a charge. And for the purposes of calculating formal charge, carbon owns 1 electron from each of these bonds. Carbon is normally group 4, and it owns only 3 electrons, so it's lost 1 and therefore has a positive charge. So that's a faster way of doing it. But again, everybody has their own method. What I don't want to see you do, because it's just too time-consuming, is to calculate formal charge for every single atom. If you know the honk rule, then you know hydrogen has 1 bond, carbon has 4. And so if carbon has 4 bonds, then it won't have a charge. And I don't want you to spend the time to calculate formal charge for that. And if something has a formal charge of 0, we don't put a 0 there. We just leave it off, OK? Question?
Does sapling accept it that way? Or
sapling accepts it that way also. All right, so Again, the formal charges are definitely on the atom rather than in the brackets. The brackets indicate resonance structures, and that's a resonance arrow. And so we left off trying to draw the hybrid. Now, in sapling, when they have you draw hybrids, they include lone pairs. I find that it's especially difficult for students to draw hybrids with lone pairs because you kind of have to keep track of, well, is that lone pair going away or is it staying? So when I draw hybrids and when you draw hybrids, you don't have to include lone pairs, okay? It makes it a little bit easier. So to draw a hybrid, we're going to draw a hybrid of the two of these. So any bonds that are not changing, we certainly are going to draw in right away. Any bonds that are changing from one to the other are going to be dotted lines. All right, so there's the first one. Notice in the second structure here, we have a double bond. In the first structure, we don't. So single bond here, double bond here. That means that that's going to be a dotted line. So like this, something like that. Excuse me? I'm missing a stage. Oh, yes, I am. Look at that. Thank you for catching that. So we have CH here. We have our oxygen, our hydrogen. This is a dotted line. So it's a partial bond. That's not a full carbon-oxygen double bond. It's not a single bond. If you took a look at this molecule and you measured the length of that bond, it would be in between a single and a double bond in length. And that's why we know that we have this hybrid here. We also want to look at charges. And you'll notice that charges up here, we have a positive charge on this carbon here. It's no charge here. So that means it's going to be a partial positive on that carbon. On the oxygen, we have a neutral. Oxygen, we have a positive charge here, so this is a partial positive. All right, so what this means is that the full positive charge is shared between two atoms. So shared between carbon and oxygen. So what we can say is we have a delocalized charge here. We have a delocalized charge, and we have delocalized electrons. And whenever we have delocalized electrons, it's going to make the compound more stable. All right. So what we're going to do on Friday, I was going to do it today, but I wanted to get a little more deeper into the drawing Lewis structures and resonance structures. What we're going to do on Friday is I'm taking a problem of this kind, this type, straight off of last fall's midterm. And we're going to work on it in class, and you're going to turn it in. So I want to do like one activity a week where I take problems that are similar to the midterm or exactly like the midterm. This time I'm taking one directly off the midterm. That gives you practice in working a problem without having answers in front of you, and it also gives you a really good idea of the type of test questions I ask, because that's what I really try to do. I don't really try to surprise you on tests. My tests are pretty predictable. All right, important points about resonance structures. Resonance structures are not real. We don't have two completely different compounds that are going back and forth. If we did that, we would use equilibrium arrows. And we're not using equilibrium arrows, we're using resonance arrows. An individual resonance structure does not accurately represent the structure of the molecular ion, only the hybrid does. Resonance structures are not in equilibrium with each other, as we mentioned. And they're not isomers. Two isomers differ in the arrangement of both atoms and electrons, whereas resonance structures differ only in the arrangement of electrons. So in a resonance structure, when you're going from one to the other, all the atoms stay exactly where they are. You're just moving electrons. When you have ions, you have atoms moving. So and you have atoms moving around in addition to electrons. Okay, so here's an example right here. And you can see that if we go like this and we use this arrow pushing, we have the arrow come from this pi bond and move on to oxygen. We get that resonance structure. So these are two resonance structures because we're just moving electrons to go from one to the other. So electron pair moves to a different location. Therefore, these are resonance structures. In the second example on the right, you can see that we have a hydrogen here bonded to oxygen. And in the compound on the right, that hydrogen is no longer bonded to oxygen. We've moved that hydrogen over here. So in this case, that an atom is moving to a different location. So this is a particular type of, these are particular types of isomers called constitutional isomers. And that's the term we're going to use. There's other types of isomers that we're going to talk about coming up in Chapter 5. But these are constitutional isomers. Different atoms bonded together. The atoms are bonded together differently, but the same molecular formula. Question?
What was the MF?
Excuse me?
What was the MF?
Molecular formula. All right, another point I want to make about these two resonance structures, they are not equivalent in energy. We would call this one the minor resonance structure. And this one here is major. So one of the things you need to be able to do is, number one, draw resonance structures, and then be able to determine which one's major, which one's minor. And so how do we do that? There's some rules for this. What makes a good resonance structure? The best resonance structures are the most stable. Look for the following structural features in order of importance. So I want to emphasize the in order of importance, so I'm going to write it again at the top here. In order of importance. Rule number 1 and rule number 2 always seem to go together, so that should be just rule 1 together. Resonance structures with more bonds and fewer charges are more stable. And resonance structures which every atom has an octet are also more stable. So those, in order of priority, that's the most important thing, is that everything have an octet and that we've maximized the number of covalent bonds. Rule number 3, resonance structures that have placed a negative charge on a more electronegative atom are more stable. There is a tendency of students in this class to come in and look exactly just where the charge is to determine which one's the best resonance structure. That's the third thing you look at. The first two things are more important. Okay, so let's go back to this example right here and see what that looks like. So over here we have fewer covalent bonds. You see how we have an extra covalent bond here? More bonds and fewer charges. Okay, so fewer covalent bonds. That's rule number 1. Here we have 7. Over here we have more covalent bonds. Here we have 8 covalent bonds. Rule number 2, resonance structures in which every atom has an octet are more stable. In this first one here, not all atoms have an octet. Carbon has no octet. Over here, all atoms have octets. So see how those two went together? When you have one less covalent bond, we very often have something without an octet. And the third thing is where the charge is. Resonance structures that place a negative charge on a more electronegative atom. So if we have a positive charge, we want it on the least electronegative atom. So here, positive charge on least electronegative atom. And here, positive charge on most electronegative atom. And I'll just use En for electronegative. So the first resonance structure has 2 things going against it. So that's a knock against it. That's a knock against it. It has one thing positive here. That's actually better, that the positive charge is on a less electronegative atom. Over here, we've got 2 things for it, 1 against. We're not just counting that. These 2 points here, the first ones we looked at, are more important. And so that's why this is the major resonance structure. So can you see if you just zeroed in on the charge, you'd get the wrong answer. Okay, so that's one of the things we want to be able to do. So again, on this page, most important. Least important. If we have 2 resonance structures and they both have the same number of bonds and both have octets, then we just skip right to rule 3 and then we look at where the charges are. Okay? We have a couple of extra ground rules here. Only carbon without an octet. So although it looks upsetting to have carbon without an octet, by the time you get through organic chemistry, you're not even going to notice when you have carbon without an octet, because we use carbon without an octet as a reactive intermediate. So when you're drawing resonance structures, it's okay to have carbon without an octet. But we never want to have oxygen, nitrogen, or halogens without an octet. Never have oxygen, nitrogen, and halogens without an octet. Now, you might find some problems in sapling where they have oxygen, nitrogen, or halogens without an octet. You will never see anything like that on any of my exams. Okay, so that's an additional rule. And never 2 plus or 2 minus charge. On any atom. And you may find a sapling problem or 2 where they, not a sapling, but a Smith problem or 2 where they have that. I will never have that on my tests. Because you can really go crazy with drawing resonance structures and having things with multiple charges and 2 plus and 2 minus. We don't want to go down that pathway. So you will never have to draw anything with oxygen, nitrogen, and halogens without an octet, and never a 2 plus or 2 minus charge. Okay, so the problem that we're going to do next week in class, I'm going to hand it out, you're going to work on it, we're going to pass it back in, and you're going to get credit for doing the problem, okay? And it's going to be something similar to this, drawing resonance structures and being able to draw a hybrid. All right, questions? Anybody? On resonance structures, formal charges, Lewis structures. Okay, We're going to talk about condensed structures. Condensed structures are a shorthand way of drawing molecules. If we drew in every atom and every bond of every molecule that we had, it would take forever. I would have to give you 2-hour midterms, and we'd have to have a 4-hour final. So we have these shorthand ways of drawing things, and it saves us a lot of time. So here's some guidelines. All atoms are drawn in, but bond lines are generally omitted. Atoms are usually drawn next to the atoms to which they are bonded. Parentheses are often used around similar groups bonded to the same atom. Lone pairs are omitted, and formal charges are shown on the atom to which they belong. And so it takes a little getting used to be able to look at a condensed structure and be able to draw a Lewis structure. We also do other things to save us time in drawing that are coming up. But let me give you an example here. This is a condensed structure. All right, so the hydrogen following the carbon, the 3 hydrogens, means that those 3 hydrogens are bonded to that carbon. And then the hydrogens following this carbon, that means that those 2 hydrogens are bonded to that carbon. Those 2 hydrogens are bonded to that carbon, and then this is bonded to a chlorine. So we would draw that, drawing out all the bonds. This would be the Lewis structure for that. Okay, remember Lewis structure, we always have to include the lone pairs. So we've left the lone pairs off. If there's formal charges, you will see formal charges on the atom to which it belongs. But that's what that would look like, and it saved us a lot of time drawing that condensed, right? That gives a lot more information. The condensed structure gives a lot more information than if you just had the molecular formula for this. This would be C4H 3, 4, 5, 6, 7, 8, 9 Cl. That's the way you draw it in GChem. And then, of course, you have no idea how those things are bonded together. This gives a lot more information. We have a shorthand way of drawing aldehydes. You're going to learn about aldehydes coming up, but this would mean that that hydrogen, because this hydrogen following the second carbon is actually bonded to that carbon. Okay, so it's not COH. So this would be let me draw the Lewis structure here. This carbon has bonded to 3 hydrogens. This carbon is bonded to this hydrogen, and this is actually an aldehyde. So that's what that would look like. So that's a shorthand way of drawing an aldehyde. We also can do the same thing with a ketone. We're going to learn the names of these compounds in one of the upcoming chapters. You don't need to know that right now, but you just need to understand what the shorthand is for that. So we have carbon bonded to 3 hydrogens. Okay, so that's what that conveys. So for this one here, it is not this. There's a tendency for students who are just learning to draw this instead. And there is a tendency for students that are just learning how to interpret condensed structures to draw it like this. And I'm just doing CH3s for these rather than drawing them out. So I'm kind of doing half condensed, half Lewis here. And we do that a lot. Okay, so this is the structure here. Let me erase this right here. This is the structure here. Not this. Okay, and that's just a matter of recognizing this is the way we draw this type of structure. This is the way we draw this type of structure. There's also one more that usually throws students off, and that's this, CO2H, or you'll see it also drawn COOH, and that's a carboxylic acid. I usually draw it like this, and that's equivalent to, and I'm going to do this kind of half condensed, half shorthand. That means this. And there's two ways that students usually draw these incorrectly. And I'll draw them right here so you can see. Or, so the red is what you don't want to do. So CO2H, or this, you'll see it drawn both ways. I draw it like this. I think there's more of a tendency if I draw it like this to draw it like that. And that's not a correct structure. And that's also not a correct structure. Notice if we draw it this way, this oxygen doesn't have an octet. There's no way we can fix that. That means it's wrong. Okay? So notice what a lot of these guys have in common here is we have structures where we have atoms next to each other, both with lone pairs. That tends to be an unstable situation. And so if you see yourself drawing these, you know you're making a mistake on the test. So now notice we have atom here, lone pairs next to lone pairs, lone pairs next to lone pairs, lone pairs next to lone pairs. And here we have no octet on oxygen, and there's really nothing we can do about it. No octet on carbon, no octet on carbon, no octet on carbon. Okay, so obviously there's other ways we can draw these structures, but this is not what this conveys. So this is just a matter of getting used to these three compounds here. Questions? Yeah?
That little corner, that's a carbon?
This little corner is a carbon, and see, I'm already falling into my pattern, so once we get used to the shorthand ways, that's a carbon right there. Yes? I don't put the last C for this top one here. Which one? Here?
Yeah. How come you don't put the last CH?
1, 2, 3, 4. 1, 2, 3, 4.
Yeah, but how come you don't condense it with the CH2 in the parentheses? Or do you just write that?
This means that I have a chain of these. So here's this CH3 is right here. This is, I means I have two CH2s in a row. CH2, CH2. Oh, why didn't I include it that? I could have drawn it that way. I also could have drawn it that way. That's also okay. I see what you're saying. She's asking whether I could have just done CH3, CH2, 3 and left this one off. That's also okay to do that. More questions? All right, so there's condensed structures. There's three-dimensional structures. 3D dimensional structures give the 3D orientation in space and all formable charges, but we don't have to put lone pairs. We can if we want, but we don't have to. So this is tetrahedral carbon, and that's a 3D, we call that 3D dash wedge. There's other names for it. We're calling it 3D dash wedge. And so any lines that are straight are in the plane of the paper. So this carbon and this methyl are in the plane of the paper. This hydrogen is going back, dash, dash, dash. That means it's behind the plane of the paper. And this hydrogen here, since it's wedged, is going out of the plane of the paper. So that's attempting for us. We have the limitations of drawing on a two-dimensional surface. And that's the best thing we can do to convey that that's a three-dimensional tetrahedral structure. All right, probably one of these days we'll be able to do something where we have that floating above the page and we'll actually be able to see that it's three-dimensional, but right now this is our limitation. So that's a 3D structure. Lone pairs are optional. Condensed structures, lone pairs are optional. The only one that requires lone pairs is what? The Lewis structure. Okay. Then there's skeletal structures, and you saw me falling into this trap. Once you get used to drawing these things in a shorthand way, it's hard to go back and draw them everything out completely. So skeletal structures are a simplified way of drawing more complex molecules, especially those containing rings. Here are the rules for skeletal structures. Assume there is a carbon at the junction of any two lines or at the end of any line. So remember, I'm kind of glad I did that here. So that was a triangle. So that meant automatically it's understood that there's a carbon at the junction of those two lines. Assume there are enough hydrogens around each carbon to make it tetravalent. Draw in all heteroatoms and the hydrogens directly bonded to them. Heteroatoms are atoms other than carbon and hydrogen. So things like oxygen, nitrogen, sulfur, halogens. Draw in heteroatoms, lone pairs are often left out and are understood. So we just get used to drawing these shorthand ways. Lone pairs are understood. That means that you understand and I understand that if I don't draw them in, you know that they're actually there. Always include formal charges. So in all these ways of drawing structures, condensed, Lewis, skeletal, 3D, we have to draw lone pair. We have to draw formal charges on all atoms that have them. Okay. So here's some examples here. This is a shorthand way of drawing this structure, and what that means, this is the same as. See how much longer this takes to draw. You'll see. I'm drawing the Lewis structure now, so I'm including lone pairs on oxygen. That's what that means. Over here, you'll see, especially for rings, it takes a long time to draw these. All right, so this carbon has a positive charge. Now we're going to draw in all the hydrogens. We're assuming tetravalent carbon. So carbon bonded to 4 different things. Because carbon bonded to 4 different things has no charge, and all of these carbon atoms don't have a charge. How many hydrogens on a positively charged carbon?
1.
1 hydrogen. Okay, so it takes a lot longer to draw this. This one right here. And look at me. See, it's so we have this. We have a negative charge on that carbon. So since all of these other carbons are not charged, that means they have 4 bonds. So the hydrogens we draw in, the hydrogens are understood. Only 1 hydrogen on this carbon because it's part of a double bond. If we drew 2 hydrogens, then the carbon would have 5 bonds. So what about here? What about carbon with a negative charge? How many hydrogens? 1 hydrogen. So that would, this is a shorthand way of drawing that. It's common to combine more than one type of structure. It's perfectly okay. It's perfectly okay to combine more than one. So for example, you will find yourself drawing this. I'm using CH3s. As we'll learn coming up, these are methyl groups. And I don't have to draw out all of those carbon-hydrogen bonds. That's a cross between condensed and 3D. Excuse me? Oh, lone pairs. I left lone pairs off here, right? See that? See how easy it is to make that mistake? Yeah. And so a Lewis structure, we have to have the lone pairs. So I do need to put that. So this one here, cross between condensed and 3D. And another structure here. Cross between skeletal and condensed. All right, and so now since this technically, and so that oxygen has two sets of lone pairs, technically I don't have to draw those lone pairs if it's not this is not a Lewis structure. If it was a Lewis structure, I would have to include the lone pairs. So let's just go ahead and throw them on here. So formal charges always required, lone pairs not always required. Okay, questions about how to draw structures? Yes? A line on top of the lone pairs. Why don't you show me that after class? I don't remember seeing that. Okay, more questions? So once you start drawing these things more simply, it's just very hard to go back and do it the long way. Okay. Determining molecular shape. A Lewis structure tells us which atoms are connected to each other but implies nothing about the geometry. We need to know a little bit about geometry so that we can predict what molecules are going to do. So what we're going to do is we're going to use VSEPR, which is valence shell electron repulsion theory to predict the geometry of a molecule. So you may remember this from Chem. So what we're going to do is we're going to count the number of groups surrounding a particular atom to determine geometry. A group is either an atom or a lone pair of electrons. So in order to correctly predict a structure using VSEPR, we need to have all the lone pairs there so we can account for them. The most stable arrangement keeps these groups as far away from each other as possible. So molecules with 4 groups will adopt a tetrahedral arrangement. Molecules with 3 groups will adopt a trigonal planar arrangement, and molecules with 2 groups will adopt a linear arrangement. So if you remember back to Chem when you were doing this, you had to do like trigonal bipyramids, sawhorse, all of that. We don't have to do that in this class. These are only the 3 things we have to worry about for our class. So I'm going to do a Chem example and then an Ochem example for each. So molecules with 2 groups. So here's my Chem example, and here's my Ochem example. So we see that beryllium has 2 groups around it, so therefore it's linear. So that means that this bond angle here is 180 degrees. Here's an Ochem example, because we don't really ever use beryllium in our class. An Ochem example here. We have a carbon here that has 2 groups around it. The triple bond counts as 1 group, because those bonds occupy the same space. So we're looking for atoms and lone pairs of electrons. So don't count the bonds and be thrown off by that. This carbon is bonded to 2 atoms. It doesn't have any lone pairs. So 2 groups. Therefore linear. We are ignoring multiple bonds. And we're going to count only atoms and lone pairs. Now we don't really have a central atom in this compound here, so each carbon is going to be linear. So that means that we have a 180 degree bond angle here. They're both 180. All right, so those are two examples of molecules with 2 groups. What about molecules with 3 groups? Classic G-Chem example here. BF3, boron trifluoride. And we'll have an O-Chem example here. So that boron has 3 groups, no lone pairs. So 3 groups. Therefore, trigonal arrangement of those groups, trigonal planar. And our bond angles are 120 degrees. So all boron fluorine bonds lie in one plane. So all BF bonds lie in the same plane. So here's an O-Chem example. If we look at each carbon separately, because we don't have a central atom, we look at each carbon separately. This carbon is bonded to 3 atoms. So trigonal arrangement of those 3 groups with respect to each other. This carbon here also bonded to 3 atoms. So both of them will be trigonal planar. And so we have 3 atoms around each carbon. So therefore, trigonal planar. And what we're going to see here is that we have approximately 120 degree bond angles. They're not going to be exact. We'll talk about that coming up later. But we have 120 degree bond angles here. And all 6 atoms lie in the same plane. Questions on molecules with 2 groups or 3 groups? Anybody? Yes?
We don't have trigonal bipyramidals?
We don't? Yeah, no trigonal bipyramidals. All right, let's do methane. So this is a vastly simplified VSEPR, right? Molecules with 4 groups. So we have methane. Here's our Lewis structure. So before you use VSEPR, you want to draw a Lewis structure, which means that you want to draw all the charges, you want to draw all the lone pairs so that you don't make a mistake. 4 groups around carbon. So that means that the groups are at the corners of a tetrahedron. And so here we have in the center in the center of the tetrahedron is carbon. So carbon at the center. And all 4 groups, which in this case are hydrogens, are at the corners of a tetrahedron. So we would call this molecular shape. Would be tetrahedral. This right here would be a ball and stick model of methane. And so if you drew a line connecting that bond here, that would be this. And this is the line connecting this hydrogen here, just like that. And this is the line connecting these 2 groups here. Would be that. So this is the 3-dimensional orientation of carbon, which shows it's a tetrahedron. And if you actually had this in your hand here, this bond right here is in the plane. This bond is in the plane. This bond right here, can you see that that would be jutting up out of your paper? And this bond here would be going back into your paper if you had it. Again, I'm looking forward to the day that we can have that lift up and be floating over our page. That would be amazing. So if we want to draw this using our limitations of drawing here, we would draw this hydrogen and this hydrogen here in the plane. And this hydrogen here is going back into the back of the plane of the paper, and this hydrogen here is coming forward. So that's how we would draw that 3D dash wedge. So we have a three-dimensional orientation in space. Bond angles, remember bond angles for a tetrahedron? 109.5, right? That's the bond angle there. All of 4 of those bond angles are 109.5. All right, let's look at a few other common things that we will use in our organic chemistry. This is ammonia. And here we have a lone pair on nitrogen. So nitrogen has one lone pair and 3 hydrogens, so 4 groups all together. So here again we have our Lewis structure. Four groups around nitrogen. Therefore, the groups are at the corners of a tetrahedron. So notice I've even put the lone pair at one of the corners of the tetrahedron. So what would we call this molecular shape?
Tetrahedral? Oh no.
I heard a tetrahedral. What else? What else would we call this?
Trigonal.
It's a trigonal pyramid. So when we're naming molecular shape, we don't include the lone pairs. It's basically what it is if you took a picture of that molecule and the camera cannot see lone pairs, what would you call that? So what this would look like is if I uncover that, right? Wouldn't this look like that? Look just like that. So we wouldn't call that tetrahedral because we're not seeing the lone pair. We would call it trigonal pyramid. So there's a lot of confusion in terminology, molecular geometry, electron geometry, and there's always confusion on exams. So I'm going to use the word molecular shape when I want you to name it the actual shape where you don't see the lone pairs. They're there, but your camera, you took a picture, it can't see it. Okay? So if we want to draw this 3D dash wedge, it's going to look like this. And that's really what we're naming. We're naming this. That's what that looks like. That's what that looks like when we take away that bond. Bond angles here are going to be a little smaller than the bond angles for a tetrahedral atom. So 107. So this is our 3D dash wedge. And the bond angles are smaller than 109.5. Anybody know why that is?
It's the bond, it's the lone pairs on the bottom pushing it down.
Yeah, the lone pairs actually take up more space than a bond. Remember, these groups of electrons, we've got 4 groups. They want to get as far away from each other as possible. And it turns out that the group with the lone pairs, there's more repulsion that actually takes up more space, so it pushes the hydrogens away further and condenses that bond angle. So why lone pairs take up more space? All right, we'll stop right there and we will continue this on Friday.